Now we'll be looking at another technique, that is impulse invariance method. Steps to design a digital filter using impulse invariance method is: for the given specification, find the HA of S, the transfer function of an analog filter. Select the sampling rate of the digital filter, that is t seconds per sample. Express the analog filter transfer function as the sum of single pole filter, that is HA of S is equal to summation of k is equal to 1 to n Ck divided by S minus Pk, where Ck is the coefficient in partial fraction expansion. Pk is the poles of the analog filter. Now compute the Z transform of the digital filter by using the formula. H of Z is equal to summation k equal to 1 to n Ck divided by 1 minus e raised to Pk into t into Z raised to minus 1. So for high sampling rate, you need to use this formula. H of Z is equal to summation k equal to n t into Ck divided by 1 minus e raised to Pk into t into Z raised to minus 1. Let's look at the problem on impulse invariance. For the analog filter transfer function, H of S is equal to 2 divided by S plus 1 into S plus 2. Determine H of Z using impulse invariance method. Assume the value of t is equal to 1 second. The given transfer function is H of S is equal to 2 divided by S plus 1 into S plus 2. Using partial fraction, H of S is equal to A divided by S plus 1 plus B divided by S plus 2. Now we need to calculate the value of A and B individually. So in order to calculate the value of A, only A, it is H of S is equal to A divided by S plus 1. So A is equal to H of S into S plus 1. So here we need to substitute the value of S as S is equal to minus 1, and we get the answer as 2. Similarly, we will be calculating the value of B, that is H of S is equal to B divided by S plus 2. Therefore B is equal to H of S into S plus 2. Here the value of S is equal to minus 2. Substitute the value and you get the value of B as minus 2. Therefore H of S is equal to 2 divided by S plus 1 minus 2 divided by S plus 2. Now the next step, here H of S is equal to 2 divided by, the denominator can be written as S minus of minus 1, which is nothing but your S plus 1. Similarly, minus of 2 divided by S minus of minus 2. Using impulse invariance technique in the equation, so this is what the transfer function we have found. H of S is equal to 2 divided by S minus of minus 1 minus 2 divided by S of minus 2. Now we will be using impulse invariance technique. So H of S, which is, this is in analog form, and we are converting that to digital form by using impulse invariance technique. So here S minus Pk is transformed to 1 minus e raised to Pkt into Z raised to minus 1. So here there are two poles, S minus Pk, so P1 and P2. P1 value is minus 1, P2 value is minus 2. So H of Z can be written as 2 divided by 1 minus e raised to, the value of P1 is minus 1 into t into Z raised to minus 1, minus of 2 divided by 1 minus e raised to minus 2t into Z raised to minus 1. So here the value of t is 1 second. So we get the answer as H of Z is equal to 2 divided by 1 minus e raised to minus 1 into Z raised to minus 1 minus of 2 divided by 1 minus e raised to minus 2 into Z raised to minus 1. Here the value of e raised to minus 1 is 0.367. Value of e raised to minus 2 is 0.135. Substitute the value of e raised to minus 1 and e raised to minus 2 here. We get this. Cross multiply the numerator and the denominator, and the last expression you get is H of Z is equal to 0.464 Z raised to minus 1 divided by 1 minus 0.502 Z raised to minus 1 plus 0.0495 Z raised to minus 2. So here in this problem he has given you the direct transfer function and find the poles, convert that poles to the digital filter and simplify. Now we'll be looking at one more problem. A distal low pass filter is required to meet the following specification. 20 log of h of omega, where the value of omega is 0.2 pi, less than or equal to minus 1.9328 dB decibel. 20 log of h omega, where the value of omega is 0.6 pi, less than or equal to minus 13.9794 dB. The filter must have a maximally flat response. Find h of z to meet the above specification using impulse invariance transformation technique. Now the given specifications are here. This value represents the value of alpha p. This one. So the value of alpha p is minus 1.9328, which can be written as kp also. In some textbooks they refer the value of alpha p as kp. So here the value of alpha p is minus 1.9328, value of alpha s is minus 13.9794, and the value of omega p is 0.2 pi, omega s is 0.6 pi. Here in this impulse invariance, the relationship between the analog and the distal filter frequency is omega is equal to omega t, where the value of t is assumed to be 1 second. Therefore, the analog frequency is equal to the distal frequency. So we need to convert that distal frequency to analog frequency first. So omega p is equal to directly 0.2 pi radians per second. Omega s is equal to 0.6 pi radians per second. Whatever value of omega p and omega s are there, that will be the same for analog frequency. And as usual, the value of alpha p is minus 1.9328 dB, alpha s is minus 13.9794 dB. Now we need to design an analog low pass Butterworth filter, that is HA of S. So here we need to calculate the order of the filter. So for Butterworth filter, this is the formula. Substitute the value of alpha s, alpha p, omega s, omega p. The value of n is 1.70. Now the next step is that rounding off the n value to the next higher integer, we get the value of n as 2. Now depending upon the value of n is equal to 2, the transfer function of a normalized Butterworth filter is h of s is equal to 1 divided by s square plus root 2s plus 1. Now we have to determine the cutoff frequency. Cutoff frequency formula is omega s is equal to omega p divided by 10 to the power 0.1 into alpha p minus 1 whole to the power 1 by 2n. So substitute the value of alpha p and n and omega p, we get the answer as 0.726. That is the value of cutoff frequency. So this process we have seen in designing a normalized analog Butterworth filter. Now once the transfer function is found and the value of cutoff frequency is calculated, we need to apply low pass to low pass analog frequency transformation. So here h of s is equal to 1 divided by s square plus root 2s plus 1. So the value of s is replaced by s by omega c. So the value of omega s is 0.726. So substitute the value of s by 0.726 in this transfer function, and after the simplification we get this as 1 divided by s square plus s square divided by 0.527 plus 1.94, that is root 2 by 0.726 1.94 plus 1. This will be the LCM. So we get h of s is equal to 0.527 divided by s square plus 1.02s plus 0.527. So here onwards, this is very important part in order to find h of z from h of s. So till now it is ha of s only. Now factorize the denominator and we get, if you factorize this denominator, s1 is equal to minus 0.51 plus j of 0.517, s2 is equal to minus of 0.51 minus j of 0.517. Now the h of s can be, denominator can be written as 0.527 is same as the above expression. The denominator can be written as, numerator expression is same as the above function, transfer function. The denominator can be written as h plus 0.51 the whole square plus 0.517 the whole square. So this is nothing but your a minus a plus jb. This is minus a minus jb. Right. So you are trying to write this as s plus A. So that is nothing but S plus A minus JB into S plus A plus JB, that is S minus S1 into S minus S2. So here this is assumed to be A, this is B, this is A, this is B. So it is A minus B, A plus B. So this expression is written as S plus 0.51 the whole square plus 0.517 the whole square. Now we'll be taking 0.517 and we are going to multiply and divide both to the numerator and denominator. So now divide 0.527 by 0.517, we get 1.019 into 0.517 divided by S plus 0.51 the whole square plus 0.517 the whole square. So this is the expression of analog filter. Now we are going to convert that H of S to a digital filter. So design H of Z with t is equal to 1 second, applying inverse impulse invariance method. So B divided by S plus A the whole square plus B square. This expression can be written as e raised to minus at sin bt z raised to minus 1 whole divided by 1 minus 2 into e raised to minus at cos bt into z raised to minus 1 plus e raised to minus 2at into z raised to minus 2. So here you can see that the value of B for the numerator and the denominator should be the same. So this is what we have met with this expression. So here S plus A the whole square. So the value of A is 0.51. The value of B is 0.517, which is there on numerator as well as the denominator. So accordingly you have to substitute the value of A and B in this formula. So we get H of Z is equal to 1.019 into e raised to minus 0.51 into sine of 0.517 into z raised to minus 1 divided by 1 minus 2 into e raised to minus 0.51 into cos of 0.517 z raised to minus 1 plus e raised to minus 2 into value of A is 0.51 into z raised to minus 2. Again, when you are calculating value of sine and cos, you have to keep the calculator in radian mode. So you get the answer as 0.6 into 0.494 z raised to minus 1, 1 minus 2 into 0.6 into 0.869 plus 0.360. Multiply this. Multiply 1.019 into 0.6 into 0.494, you get 0.302. The denominator is 1 minus this whole expression is 1.042 z raised to minus 1 plus 0.360. So this is how we have to solve the problem for an impulse invariance method technique. Thank you.